So today we're going to talk about one of the most fundamental things that you have to learn when you're learning chemistry, and that is how to balance chemical equations. So realize that there's some things here that we're going to combine. We've already talked about how the law of conservation of mass is something that tells us that matter is neither created nor destroyed. And what this means in a reaction is that whatever we put into the reaction must equal what comes out. You don't walk into a room with no hat on and suddenly a hat appears out of nowhere, right? So that's what we're doing when we're balancing chemical equations. We're making sure that what goes into a reaction is what comes out. And you have to keep in mind what I have over here is that when we deal with things like subscripts, so things like this and these little twos down here, remember, those came from making the formula. If you start to change that, you start to change the identity of the molecules that you're either putting in or taking out. So for example, if you start to change this O2 to O3, you go from something which is oxygen gas that you breathe routinely to something that's ozone, which would be O3, which, though it's great in our atmosphere to keep us from nasties from the sun, it's really, really, really toxic to breathe. So those are completely different formulas. We don't change the subscripts because that's a big no-no when coming to balancing equations. Instead, what we do is we add numbers in the front of the formulas in order to be able to tell what is balanced there, okay, in a reaction. So to start off with, I would say, let's say that we've got H2O2, and that's going to decompose into H2O and O2. So to begin this type of balancing of equations, I like to take account of what I have on each side. Here I know that I have 2 hydrogen because there's that number 2, and so I'll just put that in my little accounting down here. Same thing with oxygen. I have 2 oxygen and I put that in my accounting down here. And then I've got to take into account what's over on the other side. So over here we have 2 hydrogen and there's 1 oxygen on this in this water. And then we also have another 2 oxygen over here. So I didn't put this down anywhere, but here's a little secret. If you've got something that's just by itself, like O2 there, deal with him last. Worry about him last, because he's the easiest thing to do because he's not combined with any other atoms to make these formulas, okay? So what we need to find is some type of coefficient that will allow one side to equal the other. Now guys, a lot of this is just playing around and trying to see what numbers affect what. But if I worry about him last, and I know that I have 2 hydrogen over here and 2 oxygen here, but I need more oxygen because there's more oxygen on this side of the equation, I'm going to start by putting a coefficient of 2 right there in front of the H2O2. Now what that does is it gives me 4 hydrogen and 4 oxygen. So let's start by balancing out these 4 hydrogen on the other side. And I would do that by putting a 2 right here. Now let me just point out the fact that when you have a coefficient in front, like this 2, and you have a 2 down here, they are multiplied together in order to get the total number that you have. So 2 times 2, that's where I get this 4 hydrogen from right there, okay? So I have now 2 oxygen here and 4 hydrogen here. So my hydrogens are balanced. Well, cool thing is, now I'm going to go back and look at the oxygen. I have 4 oxygen on this side of the equation, and the fact that I have 2 over here and 2 over here means that I have a total of 4 oxygen on the other side of the equation too. So we're good. Everything's fine here. And that means that this equation is now balanced, and what goes in is equal to what comes out. So what our balanced equation actually looks like is right here, right there, okay? And so that's what a balanced equation looks like. Sometimes you might come across a type of problem where you need to use halves. Now, truth be known, you can't have half of an atom, you can't have half of a molecule. But we can use halves or thirds or whatever it may be as placeholders temporarily if you find that that's something that's working for your balancing of equations. So for example, we've got this problem down here, and we're going to take C2H6 and react that with O2, and it's going to give us CO2 and H2O. Well, I'm going to take first account of the carbons and the hydrogens and the oxygens, right? And then you see here in blue, I took account of what we started with oxygens, hydrogens, and carbons on the right side. So to start things balanced, I noticed that over here I have 2 carbons, and over here I only had 1. So I went ahead and put a coefficient of 2 up there. And when I did that, you have to keep in mind this is not just going to change the coefficient for carbon, but it also will for oxygen. And 2 times 2 is where I got this 4 from. Okay, well, I also know that I have 6 hydrogens on this side. Remember how we're going to leave oxygen to last because it's by itself and in everything. So we got 6 hydrogens on this side. I want to affect this side, make it have 6 hydrogen. So I put a 3 coefficient in front of that, which will give me the 6 hydrogen that I need. And it also gives me 3 oxygen. So if I total together the 2 forms of oxygen here, I end up with 7 of them. Well, I have O2, so that's a problem. But if you go ahead and say that I have 7 of these halves, so right, 7 halves would actually give you 7. So I did that math right there. That's totally fine. If this isn't the way that you think of it, you can immediately double everything. They both end up with the same answer. Because here's what I mean with this. Let's say that we have an understood number 1 right there. And this we have as 7 halves, and this we have as 2, and this we have as 3. We can't have a half. We need whole numbers. We need the lowest whole number possible. So here's what we do. We take this number in front and we double it. And that's going to give me this 2. And I take this and I double it. And the reason why I'm doubling everything is to get rid of this half on the bottom. And that gives me 7. And I double this 2 and it gives me 4. And I double this 3 and it gives me 6. And now everything's balanced. Everything's in harmony. And yet we have no fractions. It's the lowest whole number we could get. Okay? So that's something to keep in mind when you're balancing. I think that you probably have seen balancing before. There's a whole worksheet on balancing if you're in my class. And you can work on those some more for sure. Just to let you know, there's other types of symbols that you will see in reactions. We have things like things that denote the state of matter. So if you see this in parentheses, S, that means solid, L is liquid, G is gas, and AQ is aqueous. That means it's dissolved in water, by the way. A lot of reactions in inorganic chemistry you'll see as dissolved in water, but there's a lot of reactions in other types of chemistry that are not. Okay. This little triangle means heat is added. Now, be aware that sometimes I put like these 3 dots in my notes, and that's from a math term, and that means therefore. That's a little bit different. But this guy is heat, okay? And oftentimes you'll see that you have heat above a reaction symbol like that. Well, what that means is that you heat it up, and that's what leads to the products in the reaction. Also keep in mind that you can add energy either as a reactant or it can be produced as a product. So there's different ways to get that energy in there, right? Okay. So next I want to talk about ionic and net ionic equations. So this is a kind of way to track what your active players are in a reaction and separate out things that are called spectator ions. Now, spectator ions is an actual term, believe it or not, but they are what they sound like, and that is they're things that are just watching the reaction take place but not involved in it taking place itself. So let's start with just a basic equation. So the molecular equation is what you're probably used to seeing by now when we're doing balancing equations. And that is you have one thing react with another. And notice that these are double displacement reactions, which those we are going to look at a little bit next lesson. But basically all that means is that this positive over here reacts with this negative, and this positive over here reacts with this negative. And see, the AgCl is like they switch partners. And the NaNO3 comes from positive, negative, okay? And so this molecular equation tells us a lot of more information as well. For example, I can tell that we start with both of these in an aqueous solution, but this AgCl that you get out as a product is solid. In other words, this is a precipitation reaction. It's something that gives you a solid stuff at the end, and this stuff is still dissolved in water. So we break this down into two different types of reactions. The first is known as the ionic equation. And here all we do is we separate out the ions, but you leave the things that are solid stuck together. So here's what I mean. There's the solid that's stuck together. He's still all one. Everything else gets to be positive, negative, whatever it's supposed to be. So it gets to be its charge that it's supposed to be. Again, the reason why you need to know your polyatomic charges, okay? So Ag positive plus NO3 negative, both of those are aqueous. And then you add that to Na plus aqueous and Cl minus aqueous, and you get this AgCl. But you also get out Na plus and NO3, and both of those are aqueous. So going from an ionic equation, we could do something called a net ionic equation next. And what that does is it takes our ionic equation, and anything that's the same on both sides gets canceled out. So look at this. Those are the same. This NO3 is over here. That's the same too. These are not the same because they make a solid product. And these are the guys that end up making that solid product. So the ones that I've underlined in red are the ones that I kind of call the active players, right? Because this and this equal that. That's really all you're writing down when you come to a net ionic equation. The ones that I struck through, Na, NO3 on both sides, those are the spectator ions. They're just watching the other stuff there. They're just watching the other reaction happen. But guys, you can't go weigh out a bunch of Ag plus and a bunch of Cl minus. You can't, because the world doesn't work like that. We don't have formulas with positives hanging out by themselves and negatives hanging out by themselves, because it just doesn't work like that. So that's why we need those spectator ions in order for everything else to happen. Kind of cool. So keep that in mind. So reactions that form solids are called precipitation reactions, and the solid is what we note as the precipitate, and this can sometimes be also abbreviated as PPT, which I know is like a PowerPoint, but that's what we say. There is a way to predict what will precipitate in water when you do those double displacement reactions. So in other words, when you switch partners, and those are from the things called solubility rules. Every book has something slightly different. Yes, you have to know these. There's several variations. Use the one that's in your textbook. I don't care how you commit that to memory, commit it to memory, okay? One little point else that we should talk about. When you have charged ions in solution, like, oh yeah, all the stuff that's got charged to it up here in the ionic equation, those, if you put it into solution, can actually conduct electricity. Super cool to watch a light up when you have just basically a light bulb in the water. Strong electrolytes are things that nearly dissolve into ions completely. In other words, instead of sticking together like this, they separate into something positive and something negative. Some things will fully do that, or what we call fully disassociate. Other things, on the other hand, will say, you know what, I'm for some of this to go that way and give you the positive and negative, but I kind of am okay staying this way too. And sometimes you'll see arrows going back and forth like that. Or another way is to go like this. Okay, those mean the same thing. But what that's saying is that, hey, not all of it goes to this side. Some of it stays as on this side too. And so those would be weak electrolytes. So a small amount goes to the product side over here. Okay. You also have things that are non-electrolytes. For example, sugar dissolves in water, but it's not a salt. It's not an ionic compound. And so you're not going to have something charged there and it won't conduct electricity. Just because it dissolves does not mean you have a positive, negative type of interaction there, okay? Cool. See you on the next lesson.